Welcome everybody. Today I'm going to be talking about some developments that my team and I have made on ensemble classification with the use of error-correcting output codes and matrices with alternative number bases. So we're going to start off with some background on ECOC ensemble learning, as well as some previous research and motivation for our project. Then we'll discuss some new ideas that my team has developed together, as well as experimental results from these new ideas. So to begin, in ECOC ensemble learning, instead of training a single classifier on a large number of classes, we assign a code word to each class and place those code words in a matrix. Then we generate a classifier for each column of the matrix, where each number in the column is associated with a single class. In order to classify a new data point, we run it through each classifier and calculate the distance between the resulting code word and the word for each of the original classes. To do this, we use Hamming distance. For the purposes of this experiment, we define Hamming distance as the number of elements that differ between two code words of any number base. In this example, the distance will be 3 because there are 3 differing elements. In order to optimize this type of ensemble learning, we considered a few attributes which would be theoretically desirable in an ECOC matrix. First, classes that are farther apart are easier to distinguish, so it's important that rows of the matrix have the maximum Hamming distance possible. It's also important that classifiers are independent, because redundancy causes unnecessary computation, and it defeats the purpose of using multiple classifiers. A crucial note is that columns don't have to be identical to be redundant. For example, the 2 red columns of this matrix will result in the same classifier because they're complements of one another. Researchers in the past have found that using higher number bases in ECOC generally has better results than binary classification. The people who determined this were using randomly generated matrices filtered by Hamming distance. One large caveat for this method is that the calculation time for Hamming distance between every set of rows and columns in a matrix grows exponentially as the size of the matrix increases, so it's very computationally expensive to find an optimal codebook. To solve this problem, we've discovered a deterministic construction for matrices of prime number bases that is comparable to those that are randomly generated. It's been pointed out before that Hadamard matrices are ideal for binary ECOC because the distance between any 2 rows or columns is always half the width. By definition, there aren't any complements, and the distance between the classes will always be large. There's a recursive construction that can generate Hadamard matrices with a size of any power of 2. In this case, we define H' as the matrix in which all 1s in H become zeros and all the zeros become 1s. To expand this construction to higher number bases, we began with ternary codebooks. Here, m plus 2 is the matrix where 2 is added to every element of m, and then we do a modulo by 3. The Hamming distance between any 2 rows or columns of these matrices is always 2/3, which is higher than anything possible with binary codebooks. The generalization of this ternary construction that we developed can generate optimal codebooks for any prime base. To make this construction, we begin by incrementing a single number along the diagonal. Then, we continue to move to the next diagonal in either direction, incrementing each time and performing a modulo by the number base. The discovery made about this method is that for any prime base n, the distance between any 2 rows or columns in the generated matrix is n-1 over n times the width of the matrix. For our experiment, we used 6 datasets with a varied number of samples, features, and classes. The most important distinguishing factor for ECOC learning is classes, because datasets with a larger number of classes require larger codebooks. In this presentation, I'll be showing results mostly from pen digits, letter recognition, Australian Sign Language, and the Alloy dataset, because they each have a significantly different number of classes. For each dataset, we selected 2 codebooks for each prime number base, one with our new recursive construction, and one that had the best total Hamming distance out of 1,000 that were randomly generated. The machine learning models we used to test our codebooks were Support Vector Machine and Decision Tree, both of which were created via scikit-learn in Python. This first set of graphs shows the relationship between performance with randomly constructed square codebooks and with the codebooks generated using our recursive construction. It's important to note that the y-axis on each of these graphs is generally very small, which means that there's only a marginal difference between the 2 accuracies. Even so, deterministic construction outperforms the random construction in most cases. In the second set, we explored the difference between performance for codebooks that have a different number of columns than rows. Codebooks with smaller widths are associated with fewer classifiers, and those with greater widths have more. In general, we found that increasing the number of classifiers is beneficial, but there are diminishing returns after it becomes large enough. Here is a summary of all of our results for binary and ternary codebooks. What stands out here is that ternary outperforms binary in almost all cases, and that the deterministic construction is generally comparable to or better than the best random matrix of 1,000. So in summary, we found that our new deterministic construction has comparable results to randomly constructed ECOC matrices, and that increasing the number of classifiers resulted in a higher accuracy. In the future, we'd like to explore the possibility of finding optimal constructions for codebooks with non-prime bases and truncating our codebooks in alternative ways in order to increase accuracy. Thank you.